And here's the outline of my talk. First, I will very quickly go through the current status of the jet physics and the RFC from both the gliders from both the theory side and experimental side, and then brainstorm the opportunity for usage of the jet physics to probe the TMDs. I'll give two examples trying to highlight the advantage of using jets in studying the TMD physics. One is using the jet substructure to study the things like TMD fragmentation functions, and the other one talking about jet imbalance. I'll start with conclude. Okay, so why jet physics? Because we're interested in jet physics these days, because most of the modern gliders are jet machines. We have tons of jets at the RC, for instance, and they are benchmark processes, such as for RC, the most typically the very first thing when you start to run the machine, typically the very first thing is to measure the digit events to get to see how well the machine behaves. So at the modern gliders, we usually have a large statistics of the jet events, and we have a better control of the experimental systematic errors. As you can see from this plot, that for instance, the jet allows us to probe QCD span over orders of magnitude in scales. For instance, here is 100 to 100 pt of the jets, ranging from 100 GeV all the way to TeV scales. And here is a projection of the EIC status. So you can see that we have pretty much events for relatively low jet PT, but that's in the bright frame for the photon-gluon fusion. And if we expect more events in the central mass frame for the IS. Okay, so sorry.
That comes out of the one paper which we did, and of course every jet which is in the second mass frame is also in the bright frame. You could just from that frame to different frames. So why do you get more jets?
That's because this is pretty much this is one order higher.
You mean with a Q square beam, you get a lower Q square beam or something?
Or what I mean is the cross section will be larger because this is RFS higher than the IS. Because this is a gluon and the photon goes to QQ bar, is actually suppressed by RFS if you compare with the IS things.
You take all, if you don't take on one process, yes.
Yeah. So that's all I mean. Okay, so people may worry about, for instance, at the RC 100 GeV is not good for TMD physics, but nowadays we have more modern techniques on the so-called jet substructure, which allows us to extend the scale region. So, for instance, if we look inside the jet, actually we are probing the collinear soft radiations, which allows us to push further the scales down to MeV or GeV scale. Okay, and also we have lots of modern techniques called jet trimming, jet grooming, or jet pruning process, which allows us to get rid of the contaminations coming from the pilots, for instance. And this is crucial for doing things like to test the universality of the for instance, of the TMD functions, because if you do some measurements on the E plus E minus machine and you want to see if this function still holds, at the RC you need to get rid of all those pilots. Okay. To make sure that the result is not affected by some devos you don't really want, and also by using the jet substructure techniques, at some point it allows us to distinguish between the flavors of the jets. So mostly to tell the difference between a gluon jet and a fire jets by using some techniques like machine learning. Okay, so that's on the experimental side. On the theory side, actually we have the first principle precision theoretical understanding. Okay, it's not like we cannot understand the jets. So for instance, in recent years, we have exciting fixed order predictions coming in the framework of the collinear factorization. For all those jet process like a vector boson plus one jet, This is the photon Z or W plus 1 jet, like dijet production or inclusive jet production, or jet in the DIS production. We can have next leading order or even next to the cube leading order predictions. Okay, so the precision is actually as good as the Drouin or the E plus E minus annihilation things, and it's actually better than semi-inclusive DIS, just from the precision calculation point of view. And other than the fixed order calculation, we can have resummation frameworks for the jet observables. Even though we have those very complicated jet pruning or jet trimming procedure, we still can come up with a resummation framework allows us to resum things like a jet R, or to resum the ungroomed or groomed jet shapes, for instance, the jet mass. Okay, so all in all, to say is that the precision for the jet physics, it's hard, it's challenging, but nowadays it's available. So we have lots of tools for that, so we have public code for that. So on one hand, we have precision data. On the other hand, we have precision theory. This means that jet physics can be tested with high accuracy. Okay, you may it's sensitive to minor difference in the theories. So for instance, if you have two theories, they come up with two different mechanisms trying to describe the same thing. In old days, we may just argue which one is better, but now we can just test against the data, and immediately it tells you which one is better. Okay, so here's one example. In this plot, I show a comparison for different prediction for the so-called groomed jet mass. And the black dots here are just the RC data, and for those different shapes, that comes from different predictions from different groups using different approximation. And you can see that the data error is very small. Actually, you cannot see the error bar, but it's there. Okay, so from this, you can distinguish between whether the next leading order QG fraction is better or leading order QG fraction is better. Okay, that's the major difference between these two different predictions.
NP, non-perturbative or new physics?
Non-perturbative, no new physics now.
Okay.
Yeah. So this, they use some non-perturbative model to describe the non-perturbative region. So that's why. Okay. Yeah. Okay, so that's for the perturbative thing, and for non-perturbative things. So interesting non-perturbative quantities can be extracted with confidence because we have precision data and we have precision perturbative prediction. So you can extract the non-perturbative things like a PDF. So nowadays, PDF is a sophisticated industrial DRC. Okay, we have all kinds of different groups trying to fit the PDF, and you can see the jet data. So here is actually the inclusive jet data, and all those colored curve is predictions from using different PDFs. You can see the jet data does help to constrain further the PDFs. So for PDF, we can do that. We can also do that, in principle, we can do that for the fragmentation functions and the simplest functions, and those things are actually the interesting parts of the TMD community. Okay, so jet for the TMD physics, but nowadays, our goal is trying to test those functions, non-perturbative functions, but nowadays, mostly, as you can see from the talk yesterday and this talk in the morning, mostly we are focusing on Drouin, semi-inclusive DIS, and E plus E minus so far. Right? The reason we are focusing on those processes is because they're simple, and of course the factorization theorem is well established. And of course we have lots of data for that. But as for jet physics, okay, so the factorization theorem may be, who knows, it's probably not that well established, but from the other side, it provides exciting opportunities. Okay? You will see that you can use jet to do lots of things which can be achievable by Drouin by all those simple processes, but also you can test those effects which cannot be probed by those processes. And also, as from the fixed order calculation side, the jet physics, as we see before, because we also achieve next leading order or even beyond, from the fixed calculation point of view, they're the same. They're as good as those processes. Okay, lots of data so far, but so are the jet processes, and also we have lots of options.
Do you have to look calculation for this?
Well, what?
Do you have to look calculation for this?
Depends on your process. For dijet, yes. For trijet, no. But for dijet 2 means that you can have at least at the most 4 partons in final state. Yeah. So nowadays, dijet, single inclusive jets, DIS jets, or the vector boson plus jets, and the Higgs plus jets, they are known to or next leading order. Also, I need to mention that here next leading order is fully differential. So fully differential in all kinds of jet kinematics. So you can directly compare the experimental results with the fixed order calculation. Okay, you can apply any infrared safe cuts on your calculation without any problem. It's fully differential. Okay, so jet. So here, just trying to pass the message that jet is as good as those processes. And actually, to use jet to probe TMD is not a new thing, I think, to this community, is because there was decade ago, there was pioneer works by Jian Wei and by Werner Vogtsang and by Feng on the dijet, and also by my chair on the photon plus jet, to probing the TMD, interesting TMD phenomenology. And of course, modern jet will offer us more. Okay, so for instance, in modern jet, we can talking about global TMD. I will explain what global TMD is, but also we can use the inkjet substructure techniques, trying to see how much we can gain. And also we can define TMD with all kinds of different axes. We can define TMD, we can define the imbalance with respect to the beam or jet axis, and we can define with respect to the photon, which is recoil against the jet. Okay. And because we know that for jet physics, if you really look into the non-perturbative region of the TMD factorization theorem, people always said that the factorization theorem actually breaks down by Roger Somoda and Chu and Collins. But from the other side, you can see that by using this jet, if we can come up with some factorization theorem of the jet imbalance thing, based on conventional factorization techniques, we can probing the factorization breaking effects. Okay? Because all those things, you will see that all those things can be predicted to very high accuracy. So any deviation from the data will tell you it's a factorization breaking effects. So at the moment, we are not, so with this, we are not going to argue something, okay, just to argue, but now it's really tested against the experimental data to nail down if it's there or not. So here is some example. Now I come to some example. I start from the jet TMD in jet TMDs. So what we do is to trying to measure the hadron inside the jet, to try to measure the hadron a small transverse momentum with respect to the jet axis. Okay. So it knows a long time ago by Feng is that it's an alternative to the quark transversity than the semi-inclusive DIS. And also, as you can see from this morning's talk, it provides the possibility for the Gluon TMD implementation functions by control the jet BT. You see that, and of course there is more experimental controls. For instance, just to shrink the radius of the jet, you can reduce the contamination from the unwanted software variations. And also you see this from this morning's talk. This actually disentangle the final TMDs from the initial TMD structure. So for semi-inclusive DIS, okay, for this process, it's well known that if you want to measure the TMD of the hadron, for instance, actually there is a correlation between the initial state and the final state. So there is a convolution between the initial state and the final state TMDs. But for the in-jet TMDs, the TMD PDFs will be absent. Okay, it's all collinear. You will see it's all collinear PDFs, and it gives you a cleaner probe of the TMD fermentation function. So let's start from the from what we want to do. So basically, giving a jet, it's an inclusive jet. So we're just giving the signal jet. We look inside the jet and trying to identify the hadron and trying to measure its JT with respect to the jet axis. And of course, it's a multi-scale problem in the sense that PT is much larger than PT times R, and much larger than the transverse momentum of the hadron, and forward or lambda QCD or larger than lambda QCD. So typical scales for PT is roughly 20 to 1000 GeV and the RC, and R can be chosen to be 0.2 to 0.5 or even 1. Okay, JT is for the 100 MeV to 5 GeV.
Sorry,
Yeah.
what is the definition, please?
R is the radius of the jet. So basically, you come up with some jet algorithm. You pre-given a parameter called R. So trying to see if the radiation, if the particle is falling to, if the distance between two particles is smaller than this R. If it's smaller than this R, more or less, they will combine into a jet. Otherwise, they will fall into different jets. So you can think of this R as the jet radius.
Delta phi, delta eta.
Yeah, it's delta phi squared.
The particles inside the cone of the jet.
Right, and it's weighted by the particles PT. If it's inversely weighted, it's anti-KT. If it's positive weighted, it's KT algorithm.
So for your PT, much greater than T times R, and your R from 0.2 to 0.5, so much greater than means a factor of 2 to 5.
Yeah, something like that. Yeah, you can think it's not that large, but actually, yeah, but actually, for instance, for R equal around 0.2, it has a huge effect if you don't resum this log R term or not.
So 0.2 is quite small.
Yeah, 0.5 maybe. No, it's still visible. In the sense that if I just do a fixed order calculation, or if I try to resum R, you see a shift. You see a clear shift in the prediction.
With an R of 0.2, you would have exactly one particle inside the jet.
Yeah, but here,
I'm not sure what that means as a jet. It's not an ensemble anymore of particles. It is basically a single hard one side.
yeah, that's possible for EIC, but here I'm more talking about LHC things.
Yeah, LHC, fine, be my guest.
Yeah, that's fine. So yeah, so let me say this. In this, although the formalism is developed for small r, but in practice it's surprisingly good for large r. Okay, even r goes to 1, the formalism is still good. If you just do the expansion and then you compare with the full next leading order or full next leading order prediction, you will see the formalism is very good.
That's for HE.
That's for LHC.
Actually, I think the underlying physics that by defining jet, you require the PT energy for the jet much larger than the mass of jet. That's a minimum requirement to define jet. And now we do the secondary summation. You say, okay, the bare mass jet of the jet is sufficiently large to become a perturbed scale. So then you do say, okay, I do the next calculation for the TMD.
Right.
That's an underlying physics requirement.
Right.
And then the question is how large the R, because most of the particles, because of collinear radiation, dominated by collinear radiation, even though you choose R close to 1 compared to 0.7, the difference in the particle is much less. The energy carried by particle, the actual phase space you included, is much smaller than the energy already included in the middle part of the jet. So in that case, that approximation is really good.
Yeah, that's true. So there are all kinds of different ways to test how good the small r approximation. So for instance, you can do a resummation, and you expand to, for instance, next leading order, and then compare with the full next leading order calculation. You can see the agreement is very good. Also, as Janwei said, so basically you can run PCA and to see if the jet is really collimated. It's dominated by the collimated configuration, as Janwei mentioned. Right. So yeah. So we have a multi-scale problem, and the bad thing it's a bad thing for fixed order calculation because it just breaks down. Okay? You don't have reliable predictions because you have log of those hierarchies. But for TMD community or for other, for instance, effective theory community, it's good because now it's a place you can use the techniques to derive the factorization theorem and to do resummation. And all those components or building blocks is universal. Okay, so basically you will see that by what's universal mean. So let's derive the factorization theorem for this. We are doing inclusive jet at the RC. So at the first step, so there is a two-step factorization theorem, as Jenny just mentioned. At the first step, because the PT of the jet is hard enough, okay, so there is no TMD physics at all. We only have collinear PDFs, then times a hard function, then times the so-called inclusive jet function. So the hard function is nothing but the cross-section for producing a hadron. Well, for producing a hadron, Platonic cross-section for producing a hadron is known to next leading order by von Wolfson. And here F is the collinear PDFs, and the G is a universal so-called semi-inclusive jet function. You can think of as a fragmentation function. So you replace the hadron fragmentation function by this jet function. So the fragmentation function, so this jet function is used to resum this log R term. Okay. So this is first step. You basically zoom out. You don't care about anything inside this jet. But this factorization theorem is only good. It's only valid when this J perp or JT is of order PTR. Otherwise, you have a new hierarchy which breaks down your factorization theorem. Basically, what you do is you zoom in the jet. If you zoom in the jet, you will see that the radiations inside the jet and the radiations outside the jet on the boundary, they're basically the same. There is no difference at all. Now, actually, because we have some constraint on this J, which we demand this J is much less than PTR, the radiation inside jet has been constrained, right? So inside the jet, actually, we only allows the soft radiation and the collinear radiations with virtuality of this jet. So we can further refactorize this inclusive jet function into a hard collinear function, which describes all the collinear radiations on the boundary of the jet, but not allowed into the jet because the virtuality is too large. The virtuality for this guy is for the PT times R, which is much larger than the J. So we have the soft radiations inside the jet. Sorry, we have the softer radiations could be inside jet and could be outside the jet, but there has to be soft. And we have this TMD fragmentation functions, unsubtracted TMD fragmentation functions. So this TMD fragmentation functions is exactly the same as the TMD fragmentation function in semi-inclusive DIS. Okay, that's the universal part. And also, the combination here, S times D, will gives us the standard TMD fragmentation functions as in series. So that's why this is a perfect process for us to test the TMD fragmentation mechanism. Yeah.
So you said that the non-derivative effects are the same.
Yep, that's what I said.
Do you have an operator definition for the soft function?
The non-perturbative for this one in the evolution will be the same. Yeah, there is operator dependence.
So there's not going to be a jet algorithm imposed on the operator definition?
There will be not.
There's not going to be a jet algorithm imposed on the operator definition?
There is a jet algorithm here,
so
but it's only in this age, because inside the jet is so collimated. Okay, so therefore.
It depends on the radio.
Yeah, there is a radius dependence, but there is no.
So there depends on the radius, depends on the jet algorithm. If I take the operator pro expansion of that, it will give me the B squared nicely, but the matrix of the multiplies also depends on the jet algorithm.
Yeah, that's true. It will depend on R.
So it always says the scale of your TMD distribution.
Yeah, but if you carefully choose your scale choice, so basically the scale choice for the software radiation will be different from the semi-inclusive DIS. And that's the, if you choose carefully, then you can make these things exactly the same. Okay, so since they are identical to the semi-inclusive DIS, then we can just revoke the semi-inclusive DIS framework. We can have, for instance, a perturbative matching onto the linear fragmentation function. We can have the analytic Solokhov evolution plus the non-perturbative input. And this non-perturbative input can be taken from a fit of the semi-inclusive DIS process. So we can have the TMD evolution from this soft collinear scale all the way to the scale mu j equals to PTR, and above that it's all just fragmentation function, just a degraph. From this, we can resum all those large logarithms. So we want to do some phenomenology, but we figure out that actually there is no data for that. Okay? At the moment, there is no ZH being measured. ZH is integrated over 0 to 1, so we cannot do an apple-to-apple comparison at the moment. So it would be great if Rick has such a method. I think it's doable. So, but in any case, we do some comparison. They are more or less qualitatively, they are more or less agree. And also, we break down the contribution into the gluon and the quark fractions, and you can see that by choosing PT, relatively lower PT at the RHC, the gluon jet will be dominant, just because the gluon luminosity is much higher than the quark luminosity for this PT range. So from this plot, you can see it's actually provide an excellent opportunity to probe the gluon TMDs. Okay. And of course, on the theory side, we can do things like we can add on Y term, just like semi-inclusive DIS, trying to extend our predictive power. But I should know that it's much easier to calculate than the global TMD case. For instance, if you want to do a global DIS and next leading order, you probably have a complicated matrix element. The next leading order, it starts to become complicated. But here, the matrix element, if you're thinking the small r approximation is good, the matrix element inside the jet is nothing but splitting kernel. It's known at least to next leading order, and it's very small. Okay, for instance, next leading order, just the PG goes to GG. Those things are tiny, teeny. So here is one example how the Y term looks like. The expression is small. It can be made further compact actually, and also the impact is found to be very small, as expected for such a small J. So here I'm talking about the unpolarized one, but it's found to be very trivial to extend to the polarized case to test the Collins effect, as you have seen in the talk in this morning's talk. So all you need to do is to change the matching coefficient to the Collins matching coefficient, change the fragmentation function to the Collins function, and change the non-perturbing mode. So that's it, and you can see there is a prediction by our by people in the audience. Okay. So some connection to the particle community on QCD side. It's called non-global logarithms. So non-global logarithms. It's discovered by Gavin Slum 10 years ago, but still young. So what's non-global logs? So basically you have radiations, you have correlated radiations. One radiation goes into the jet and the other one goes outside the jet. It's on the boundary, okay? It's all happens on the jet boundary. So for the radiations goes into the jet, there is a constraint, right? J perp has to be less than much. J perp is a constraint for this radiation, but for this radiation, the energy can go all the way to the PT scale. Therefore, there is a large hierarchy between these two, and it cannot be resummed using conventional CSS formalism whatsoever. So that's called the non-global loss in the sense that it cannot be catched by the conventional resummation procedure. But for the leading non-global log, it's more or less just times the overall factor. Therefore, for ratios for the asymmetry I just talked about, the factor should be very small. Okay, because for the ratio it just go away, pretty much go away. So the non-global loss are there, but no direct phenomenology studies now. The reason is that usually at the RC, they are looking at the kinematics, which is far from the region where non-global loss are very, very important. Usually it's very small. But in this case, because J is measured to be only 1 GeV case, so here things may be different. So here is, so by using this formalism, we can test how large the non-global log effect is. Okay, so including the non-global logs, you change the absolute normalization logs. You can see therefore in jet TMD, may provide the very first experimental demonstration on non-global logs, which may be interesting to the HAP community. So that's some relation. Of course, you can groom the away non-global logs because NGL usually are just the softer contaminations. You can groom the way, as you can see from this this paper. But to us, it's probably very hard to relate. If you groom away, you have additional operations there, so it's probably very hard to relate to the normal TMDs because the solve function entirely changes. It's a resum calculation. Of course, you can do fixed order calculation. As I said, nowadays the fixed order calculation is fully differential. You can do whatever jet algorithm you want. You can do whatever jet substructure you like.
How did you do some? How did you do
They derive factorization theorem. I think one of our. I mean this one? Oh, for this one, they resum non-global logs numerically. So they use a Monte Carlo resummation, trying to resum the leading non-global log at large NC limits. So
they are kind of we're changing somehow the hard factor in this cross section. It does not affect the shape. Do you agree?
yeah, but
The normalization of the cross section is effective. The case that this JT is much smaller than the PT, the shape as JT is not.
Yeah, that's true. Also, yeah, that's true. So basically, the non-global logs usually only change the magnitude in the peak region or in the deep in the Sotokov region. It just change that logs, but the shape more or less okay.
This is
Yeah, but well, it will. Of course, it will change a little bit shape because this product is performed in a B space, and you Fourier transform back, you change a little bit of shape. But yeah. Okay, so that's the jetting TMD. Then we'll very quickly go through the so-called global jet, the jet imbalance or the global jet TMD. Global means that you're basically sensitive to the software relations all over events. Okay, so so here we are talking about, for instance, the imbalance between the photon and the jet production, and the people are saying that the factorization is breaking down, and there is no way you can write down factorization theorem. But the problem is, what's the factorization breaking down? Breaks down means that you should first have a factorization theorem, and then you can use that to test the deviation of the data from your factorization prediction. So we come up based on SAT, we come up with a factorization theorem for the imbalance. So I'm out of time, but probably 5 minutes.
Yeah, so you can.
Okay, so here.
We have time because there's less talk, but still.
Sure. So we come up with a factorization theorem in SAT trying to describe the imbalance of this process. Okay. So the imbalance is measured with respect to the beam axis. Okay. So here in the initial state we do have TMD PDF, but in the final state everything is collinear. There is no entanglement between initial state and final state transverse momentum. So here J is the energetic jet function, only for anti-KT, So basically inside the jet, there is no constraint. We allows all kinds of collinear radiations inside the jet, but this is only for anti-KT jet algorithm. And here H is a hard function for producing partonic hard function for producing the gamma then plus a recoiled parton. So here we have the so-called global solve function, which is a wide-angle solve function radiation, which cannot resolve the small jet radius. So therefore, there is no R dependence here. But also we have collinear soft radiation, which is collinear means that the angular separation is more or less the same as the collinear radiation. So the collinear soft is soft, but also collinear. Therefore, it has, in principle, there is an R dependence here. Okay.
So your photon is fully isolated?
We assume it's fully isolated, but here it's just a photon. It's just a parton. There's no isolation console whatsoever there.
If you go beyond tree level calculation, you have
yeah.
on that radiation.
Yeah, but here we don't consider all this. We just assume we can have a well-defined photon. It's a photonic thing. So once we have this factorization theorem, everything can be calculated to very high precision, and therefore any deviation from this prediction can shed light on the so-called factorization breaking effects. So one example is the measurement from the Phoenix for the photon plus hadron Gaussian shape. Okay, so one thing is that the soft function, this global soft function can be further written or factorized into a Joule-like soft function and times a remnants. Okay, in this way, all the rapidity divergence will only appear here, and the remnants will be free of the rapidity divergence. Only the normal epsilon divergence there. And by written in terms of this, you can see the first line is nothing but the TMD. It has the same structure as Joule as long as you have the color factor correct. Okay, so everything is known to at least the next leading order, or even beyond. For instance, the Hall function is known to next leading order also. So in this formula, can resum both the QT and the R and next leading log at least. So therefore, the prediction is very precise, and again, any deviation from the data can shed light on the factorization breaking effects.
It's the same as the Joule TMDs, same up to time.
Yeah, same up to color factors. As long as, for instance, in this process, you can have quark-gluon scattering goes to Q photon, and in this way, there is in this function, you should assign a CF and a CA. It's CF plus CA instead of 2 CF there.
So it's not included in the H, it's not included in the R factor.
It's not included what? Oh, yeah, we put all those color factors into this.
Typically.
We put the tree color factor here. We could, but we put the fixed order calculation color factor there. But it depends on how you organize the color factors, but more or less. But eventually they will be exactly the same. Okay.
And for that, you can implement zero rapidity cuts, things like this for comparison to experiment.
You could, because you could put a rapidity cut on the jet. Yes. Yeah, and also PT cut. So
this for small radius or large radius?
The factorization theorem is derived for small jet radius, but as I said, in practice, it can be extended to large jet radius for no reason. I don't know why, but just practically, if you just do the expansion, you do the comparison, it's a very good approximation for a large range of PT. Yeah. So this has been found in lots of processes, actually. Okay, so and also this can be extended to the polarized case by just doing some simple replacement. For instance, the unpolarized the TMD PDF can be replaced by the transverse TMD polarized PDF. Okay, so and all these formalisms can be very easily extended to the hadrons by just noting that here you can think of as the threshold hadron fragmentation function. Then we can use that to explain or to predict the imbalance results of the Phoenix collaboration. So that's one thing. And the other thing is we can use the jet imbalance to probe the Sievert's function at the EIC. In this case, there is no factorization breaks term, but we can directly test the Sievert's function. So more or less, the cross-section can be written in terms of this way, which is very similar to what we have before. As I should say, all those components here is universal. If we want to turn from LC to EIC or to DIS, all what we need to do is to get rid of, for instance, this PDF and to replace this hard function with the DIS hard function. And of course, some color factors should be correctly assigned. So more or less you get this. Here we have assumed R is about 1, so here we don't really resolve R, and you have some, you rearrange some of the functions to get this form. And because we don't have numerics at the moment, so just stay tuned. Okay, because I'm out of time, you can just read through the conclusion. Thanks.
Questions? A question about, you comment that you could apply this to the hadron imbalance at Phoenix.
Yeah.
And that's a very naive or very simple question, but for hadrons, of course, if even if they are back to back, they don't have to have a small. The partons don't have to have a small relative transverse momentum, right? Because I mean, fragmentation is such that one hadron would come from a parton that fragments Z of some value, the other one can come from different Z. So the partons that generate the hadrons can have actually very different transverse momenta in size and magnitude, although I mean their direction could be the same, right? I mean they don't have to have near zero imbalance in transverse momentum. So that should.
So we look at the out of plane momentum.
That's right. But if you just go back to back, I think it could be just something completely collinear.
Yeah, then you're doing a vector sum. Yeah, but we're
It's a component. Yeah. That's right. That's probably.
Yeah, that's yeah. What I mean is to explain this. Basically, they are measure these P outs. So that's why we could.
Yeah. So my group was behind that Phoenix measurement, which so you're showing all this to the 3.
Yeah, they have a new result because also we figure out that P out doesn't really gives us a back-to-back configuration. You need additional. You still need additional constraint. I think in the new result they improve some additional constraint to make sure it's ready. Right.
In the second and third paper, the third one having been submitted a couple weeks ago.
Okay.
So my group, so we would be very happy to have any kind of calculation.
Yeah. So we discussed this P out and figure out P out doesn't really give you back-to-back. We realized we need additional constraint, and then we go back to your paper and find out that there are actually new paper on that. They put an additional constraint to really force you into more or less back-to-back configuration, which is a probe of the TMDs.
So one of my current students is now working on similar measurements at LHCb, looking at dihadron, Z-hadron, and Z-jet. So if you can make predictions before we get that out, that would be.
Yeah, in principle you could, because this one is quite universal. For instance, for Z-jet, the only thing we can imagine, the only thing changed is this hard function, which is known to two loops.
E706 quite a bit of P out measurements, right?
I don't know.
I think so.
I have a look at that.
I remember thinking.
What was the order of hard function you calculate?
Here?
H,
yeah. Here, in principle, you can do next leading order, but I think
what did you calculate?
Next leading order at most. Because
if you do next leading order, you must run into the version between 4 times 4.
Well, here it's different from the inclusive case. So here it's more or less just a form factor.
Yeah,
because everything should be very soft. Therefore, it's you only have loop corrections here. It's different from the previous case. Previously, I'm saying that for this one, it's really a cross section. Then you're coming to all kinds of collinear poles or whatsoever. But here, it's just a form factor. It's loop calculation. So there's no, we will not fall into the isolation problem.
If you do the cross-section type, like if you add a physical cone, like highlights, that's it again.
Yeah, for instance.
If you do that, and there's a mismatch between the real and virtual in the face space.
Yeah. For instance, if in in a full next leading order calculation for photon plus jets, okay, you will have this problem. You need to deal with that.
I have an observation. I have those slides to show that it probably explain better. But I'm a bit puzzled by the fact that the soft function here is independent of the values of the jet.
Well, this guy depends on the radius of the jet.
So the soft radiation there is the radiation outside the jet or inside the jet?
Well, for this one, it's just collinear. It can be outside and can be inside.
Next leading order is inside.
Well, next leading order because outside is dimensionless. So.
What do you mean? I mean, this is a definition of a matrix element, not of the particular order you calculate.
You could have, for example, if you go to next leading order, so 1 to 1, you get outside, and then you get another one going inside.
Right, so there is no constraint say this one has to be inside the jet. You can have a radiation here, then here. You can have a radiation split, then one's into the jet and the other one go outside.
I can accept this when the radius of the jet is small. Suppose you have a very big radius, then I think this situation can change. You cannot really distinguish, you cannot really separate the radiation inside the jet and the jet. Things get much more deep. So I think this treatment is valid only when the radius of the jet is more than enough.
Yeah, this is true only for small r approximation, in the sense that we can have a collinear, we can have a separation between so-called collinear and wide angle.
But then I expect that when you try to measure it with a radius of order 1, you should observe a deviation from this.
Yeah, you should. In principle, you should, but you never know, right? Because you never know the power correction. For instance, the power correction may be something like r squared over pi squared. Then it's small.
Okay,
so there is all kinds of
wording. I think that should be clear that this factorization works for small radius.
Yeah, you're right. I agree.
Okay.
I agree. But in practice, all what I'm saying is that in practice, people always find that even for large r, it's still valid. So no one knows why, because no one really goes to calculate the power correction. As I said, the power correction can be of the form r over some pi, then it's small. Even r equals to 1 over pi is small.
Have you made some simulation on Peter or this?
Make some approximation.
PTS simulation? Yeah.
Well, we do some we do some PCS simulation for this, and also we do fixed order check. We can do the expansion, and we can compare with next leading order, and we see it. You pretty much have a perfect agreement in the region.
Okay. Last question.
It was a comment, quick comment. That for regarding the R, why it works, there was a study where they calculated the next correction for invariant mass, and they found that the corrections they don't come as R, but as R over 2, the same as the logarithms. And they found that at least until 0.7, the soft function seems to be almost unchanged. If you do small r approximation, or if you include the r square corrections.
I have just a very quick question. So what you said is that there is a direct connection between the TMD objects that we measure in physics and these objects that you define in jet. Does this mean that phenomenologically, if you measure these, you can reconstruct the others and vice versa?
Yes. I mean, this is a universal function. So if you believe in the formalism, yes.
You need to reconstruct the function, this S function.
The what function?
You need both a D, which can be compared to the standard semi-QTAS extraction, and the S.
Yeah, we need both. I mean, only the combination here is the standard randomization function in semi-inclusive DIS, and of course, with a particular choice of the scales.
So what's the answer?
So for this one, it's exactly the same.
Yeah, for this one, they are exactly, so for this combination, they are exactly the same as cities. So you extract, whatever you extract from this process can be directly applied to cities if you're believing this formalism.
What do you mean extracting? Because you need something.
I mean, one thing is that you have a formula in which you write the convolution of atoms. But my question is phenomenologically. Do I know the D function, the TMD fermentation function from this kind of measure? And for the series one?
For series, no, this one you count it. This one for
Collins function.
Sorry?
This is the fermentation function.
Yeah, I see that. My question is, he talked about the series
And so the other one for those proton positive, those back-to-back states, you have additional shorter factor, which so that will prevent you from identifying that.
Okay.
And that's that method you have to do.
But for the fermentation function and the Collins function, they're
identical. Yeah, for the inclusive jet, for the inside jet, for the in-jet TMD, they are identical. No, with a particular choice of scale. PT times R or
So you identify Q as Q is the city is the class Q.
or J over R something. Or J over R.
But you said the PT times R is not too large.
It is large. Much larger than J.
It has to be smaller than PT though.
Yeah, it's smaller than Q, but PT is larger. So I say that R is, let's say, 0.7. PT is 20.
This limits that your evolution, right? You can only go up to some Q. But not
That's your Q.
exactly. So in normal TMDs, I can evolve to any value of Q. But in this case, you're limited because your PT times R cannot be any larger than some number.
No, for this one, no. No, the evolution is universal. So once you extract this, and you can evolve to whatever scale you want. The evolution is universal. I mean, just like you do PDF, right? You extract a PDF from one process, and you can evolve it to whatever scales you want.
He's just saying that I can go from these functions to the TMD conventional function fragmentation by identifying Q with PT times R.
Yeah, that's the initial state. That's the initial condition.
But actually, your Q is what you measure Q, right? It's a measurement. And then you experimental measurement determine how large your Q is. This is the same. So experimental measurement of PT determines whether it's scale.
So, I need to interrupt the discussion, maybe we continue.
But does that mean that if I do the measurement, I just change R to slightly the evolution of the function?
Okay, so let's thank the speaker again.